The standard model of particle physics rests on an uncomfortable foundation. To make its math work, it requires dozens of free parameters and empirical constants, numbers like the speed of light or the mass of an electron, that must be measured by experiment and manually plugged in, rather than calculated from first principles. A framework called refractive cosmology approaches the universe from a completely different starting point. Instead of an empty void dotted with particles, it treats the universe as a dynamic, elastic vacuum. Everything that happens inside it is governed entirely by fluid continuum mechanics. At the center of this framework is a principle called the macroscopic measurement axiom. Under this axiom, empirical constants are emergent geometric artifacts. We measure these specific numbers because we are localized observers measuring continuous fluid dynamics against discrete topological boundaries. To test this, the author compiled a final ledger, sorting the theory's 178 formal equations into two strict categories: 141 equations that provide relational kinematics, and exactly 37 equations that output hard, testable numerical predictions. Evaluating those 37 numerical predictions against the Committee on Data for Science and Technology's empirical measurements provides a direct test. If a purely deterministic framework is valid, it must generate these exact values mathematically without requiring us to measure them first. To start generating those numbers, the framework first separates time into two distinct variables, a concept called chronological duality. As shown in this text block, observable time is calculated by taking the absolute chronological coordinate of the background void and subtracting the acoustic fluid transit delay. Evaluating this boundary explicitly separates the absolute age of the metric from the apparent acoustic boundary. The physical origin of this boundary evaluates as a cascading acoustic nucleation within the medium. An inward wavefront geometrically ratchets to absolute fluid incompressibility, forcing the refractive index to approach infinity, while the outward shockwave expands the causal horizon. By mathematically defining the origin point of absolute time and spatial genesis, the framework strictly dictates the continuous thermodynamic cooling of the entire macroscopic vacuum. At the absolute genesis boundary, the localized topological horizon equates perfectly to the macroscopic causal horizon, establishing the absolute primordial mass limit in equation 18. Because field coupling propagates at the acoustic limit, adjacent boundaries exist in isolation until their shockwaves intersect. Because the fluid continuum is bounded by these specific spatial and temporal limits, the framework evaluates empirical constants as algebraic ratios of these states. The speed of light, gravity, and Planck's constant emerge as the localized results of projecting scalar measurement onto these fixed boundary conditions. With the structural boundaries locked, we can test the 37 numerical predictions, beginning with the fine structure constant, represented by alpha. Here, alpha is natively defined as the geometric probability of an internal acoustic strain leaking into the continuous elastic fluid. By evaluating the baseline lepton, the electron, the formula extracts the bare geometric probability, resolving explicitly to 1 over 137.466. That mathematically derived probability maps cleanly to the established empirical measurement for the fine structure constant, which sits at roughly 1 over 137.036. Aligning a foundational gauge coupling constant with pure spatial probability provides a baseline for the framework's internal consistency. It demonstrates that a value typically found through measurement can emerge natively from the geometry of the fluid itself. The framework applies the same geometric scaling to derive fundamental mass ratios, defining mass strictly as the localized topological phase gap. To find these values, the theory uses nonlinear Eulerian circulation to calculate the bare kinematic eigenstates of the continuous fluid. Applying 3D Eulerian integration to these phase gaps extracts the baseline proton-to-electron mass ratio natively. The formula evaluates to precisely 1825.95. This mathematical prediction falls slightly short of the empirical co-data measurement of 1836.15. The difference is exactly 0.56%. In terms of equivalent electron masses, the geometric calculation is missing approximately 10.2 units. If this framework is a deterministic engine, a specific 0.56% failure in predicting the mass of a baryon requires an explicit physical explanation. Before resolving that missing mass, we need to look at how this same geometric scaling derives the physical hierarchy of forces. The framework solves the force discrepancy by comparing the localized boundary focal length of electromagnetism against the massive cosmological boundary of macroscopic advection, generating gravity. Their algebraic ratio natively distills the exact strength difference, 10 to the 41st power. Force magnitude, just like mass, is entirely dependent on the specific spatial boundaries of the fluid being measured. Resolving that 0.56% error requires accounting for the difference between a bare geometric intersection and the hydrodynamic behavior of a real-world medium. The missing mass is the result of hydrodynamic inflation. In a continuous medium, a geometric boundary must expand its outer boundaries to survive the active dynamic pressure of the surrounding fluid. Simple one-dimensional algebraic geometry calculates the raw intersection, but it lacks the variables to capture this necessary physical expansion. To model the actual space the particle occupies, we must look at the total material momentum equation for the continuum. The final cross-term calculates the topological fluid vorticity interacting with the background fluid advection velocity. Bridging the final 0.56% gap strictly mandates full 3D computational fluid dynamic evaluation of these nonlinear cross-terms. The numerical deviations between bare geometric predictions and empirical data aren't mathematical errors. They are the physical requirement of dressing an idealized spatial geometry in complex hydrodynamics. The mathematical limits established here span 37 distinct predictions, locking in parameters from the exact scalar coefficient of the Casimir force down to the pion mass glass transition limit. Legacy physics models leave these parameters open, requiring physicists to manually patch the math with observational data. In this deterministic model, these 37 outputs suggest that empirical constants are not fundamental inputs, but rather the calculated results of specific fluid interactions. Macroscopic cosmology, local quantum states, and force interactions are not separate phenomena. They evaluate as the deterministic outputs of continuum mechanics operating within a dynamic elastic vacuum.